This video looks at unbiased prediction with Karima models. The previous video looked at how you could form unbiased predictions if you had an independent or a state space model. This video is going to look at Karima models and ask what do we need from these if we want the predictions to be unbiased in the steady state. So what do we mean by unbiased prediction? So we'll revisit this very briefly. We said let's assume you're in the steady state already, so your input's at a steady value and your input's going to remain at the same steady value, and also we'll assume the disturbances are unchanging. Then you would expect your output predictions also to stay at the same value. So you have unbiased predictions if at steady state you get the correct predictions, and they're biased if you get incorrect predictions. So what we want then is the output predictions must match the current steady state if you're already in steady state, and then we're not biased. Let's look then at the Karima model. This is the most common transfer function model used with predictive control. And it's used because the way it models uncertainty and in particular disturbances is fairly well reflective of what happens in a real process. Here's the Karima model then. We have A of Z times the output equals B of Z times the input plus T of Z times zeta over delta, where typically T of Z is a design polynomial rather than an actual model parameter. Now, discrete models are usually equivalent to one step ahead prediction models if you write them in difference equation form. So we can predict sample k plus 1 given sample k. If we take our Karima model, and for now I'm ignoring the t zeta over delta term, it doesn't actually make much difference, then you'll see a y equals b delta u, where capital A is given by a delta. Now you'll notice this was covered in detail in one of the earlier videos in this series, so please go and look at that if you really need to. Now, capital A of Z can be written as 1 plus A1Z inverse and all the way down to ANZ to the minus n, and B has a similar form. If I write the difference equation form, this is what I get. yk plus 1 plus capital A1 yk and so on down to an yk minus n plus 1 equals b1 delta uk plus b2 delta uk minus 1 and so on. So this is the prediction form using a Karima model, and you'll recall, if you look at the earlier video on prediction, the bit I've ignored is plus t zeta, but if we're assuming that we're at steady state and we're assuming that the disturbance is not changing, then this t zeta term is going to be equal to 0, which is why it does not affect whether our predictions are biased or unbiased, and that's why I'm ignoring it here. Okay, in the steady state, we know this. We know that yk is the same as the previous value of y, yk minus 1 is the same as all the previous values of y for a certain number of samples. Similarly, we know that delta uk minus 1 equals delta uk minus 2 and so on, i.e. the input is not changing. We also know that because capital A of Z is defined as little a of Z times delta, then if we add together all the parameters of A, we must get 0. That follows directly from the fact that delta equals 1 minus Z inverse. Now if I put these two observations together, this is what I get. I get yk plus 1 plus a1 yk and so on equals b1 delta uk plus b2 delta uk minus 1 and so on. So that's the basically difference equation form of this model. And now what I'm going to do is separate this out. If you look in this equation below, I've essentially said we've got that yk equals yk minus 1 and so on. So this term is the same as this term and so on, and therefore I can group all the a parameters together and just assuming they're multiplying yk. Similarly, I can group all the b parameters together and assume that they're multiplying delta u, but you notice here that all the delta u's are 0, so hence I've got a 0 down there. So what I've got is yk plus 1 plus the sum of all the a parameters times yk equals the sum of all the b parameters times 0. So that's my one step ahead prediction model if I'm already in the steady state. Now finally, I use this observation that the sum of the a parameters is -1. That's what we put here. And therefore, I get yk plus 1 minus yk equals 0, or in other words, yk plus 1 equals yk. And so you can see that the predictions are unbiased. They tell me that the future outputs are the same as the current output. So, in conclusion, by definition, if I use a Karima model, I get predictions which are unbiased in the steady state. And this is unsurprising because the model is based on increments around the steady state. Interestingly, however, the Karima model does not estimate the effective disturbance model. If you look at the previous video, we're very keen on giving an effective measurement of the disturbance or disturbance estimate. But when you do the Karima model, you don't need that because you're using increments. And so this approach differs from the approach in the previous video.